Now let's look at another example from Gibbs free energy to cell potential. Another example. This time we want to use Gibbs formation energy data from CRC handbook to calculate standard cell potential for the following reaction and compare with the value from standard cell potential series. Okay, this is our reaction: copper ion plus zinc metal to form copper metal solid and the zinc ion. Both copper ion and the zinc ion are in aqueous solution. So we want to use the Gibbs free energy data to calculate the standard cell potential and then do comparison with the value from standard electrode potential series. Okay, so let's check the CRC handbook, and there will be a table for thermodynamic properties of aqueous ion. And if you refer to the table, if you find at 25 degrees C for that table, mostly for 25 degrees C, you will find delta F G0, F for formation energy, Gibbs free energy, 0 for standard state. For copper aqueous ion would be positive 65.5 kilojoule per mole. On the other hand, delta Fg0 gives free energy for formation of zinc 2+ zinc ion in aqueous solution would be minus 147.1 kilojoule per mole. The signs are very important. Don't neglect sign. One is positive. For zinc, it's negative. Okay. With this information from the CRC handbook online resource, now let's calculate the reaction Gibbs free energy change. R again for reaction, Gibbs free energy, delta for change, 0 for standard state would be, if you remember, the summation of products Gibbs formation energy minus reactant Gibbs formation energy. And copper is our product, zinc 2+ is our product, and Gibbs formation energy, because the stoichiometric coefficient are all 1 for copper, 1 for zinc. So we have 1 here, minus for reactants, copper 2+ reactant, zinc metal reactant, and similarly the stoichiometric coefficient are also 1 and 1 here. So this is what we write. And then let's write the number. For pure copper solid, the Gibbs formation energy from it would be 0 because it's just pure element. And similarly, for pure zinc, the Gibbs formation energy is also 0. And then for zinc ion, minus 147.1. For copper ion, plus 65.5. So you plug the number and calculate the reaction Gibbs free energy change would be minus 212.6 kilojoule per mole. Minus 212.6 kilojoule per mole. Okay. Then remember the relationship between delta Rg0, reaction free energy change on the standard state, with the standard cell potential. Remember, with this relationship, we can calculate standard cell potential E0 to be delta Rg0 divided by NF. Don't forget the sign, negative sign here. So we plug the number in to minus 212.6 kilojoule per mole. So you have to time it by 1000 joule per mole divided by N. This case, N obviously would be 2 times F. And this is what we got, 1.10 volt. For such a overall cell reaction, the standard cell potential is positive, which means it is spontaneous and the value is 1.10 volt. Okay? Then let's check again using standard electrode potential series data. We said the anodic or oxidation half-cell reaction for this reaction would be for zinc metal to give out electron and form zinc ion. And if you check the standard electrode potential series, the standard electrode potential for this redox pair, zinc 2 plus zinc, this redox pair or for this electrode would be minus 0.762 volt versus SHE, standard hydrogen electrode. While for the cathodic of the reduction half cell, it will be for the copper 2 plus to combine with electron from the zinc to form copper metal, and the standard electrode potential for this copper 2 plus copper redox pair would be positive 0.337 volt. Positive 0.337 volt. As a result, the overall cell potential would be the standard electrode potential for the cathodic or reduction half cell, which is 0.337, minus the anodic or the oxidation half cell standard electrode potential, which is minus 0.762 volt. And minus become positive, the result would be 1.10 volt. So you see that you can get the same value using standard electrode potential series directly, or you can go back to Gibbs free energy from the table Gibbs formation energy to calculate reaction Gibbs free energy change, and then calculate the standard cell potential. And use either method, you should have the same result. Okay.